Good afternoon. I'd like to welcome you here today to the 2019 DeLeo seminar. As you know, this has now become quite a series over time. We've had a large number of them, but it's always good to have the seminar because it gives us an opportunity to see an excellent speaker and a speaker who works on topics which are in line with the with Jan. So let me just say a little bit about Jan, for whom this series is in honour of. Jan is a distinguished Professor Emeritus of Statistics and, as most people know, the founding chair of the department here. But he's also founding editor of the Journal of Statistical Software, as well as the Journal of Multivariate Analysis. He started his academic career in the Department of Data Theory at Leiden University, and he moved to UCLA in 1987. He retired in 2014, although it seems a lot shorter time than that. He's also an elected fellow of the Royal Statistical Society, the Psychometric Society, the ISI, the IMS, the ASA, and the Royal Netherlands Academy of Arts and Sciences. So it's very good to have Jan back, and it's a great event. Our speaker today is Roger Peng, who is Professor of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. His research is broad and eclectic. He works in statistical methods for environmental health, but he also is internationally known for his work on reproducible research, computational statistics, and I would say he's a statistical evangelist, one who advocates for our discipline in the public at large with great success. So we're very happy to have Roger here today, and I'd like you to give him a very large welcome.
Thank you for that nice introduction. I think broad and eclectic, that's maybe how I would have thought of Jan, actually. I'm not sure I'm worthy of that quite yet. But anyway, it's an honor to be here. I entered the department in 1999, so it's been 20 years for me. And I just a very brief time travel before I get to the actual talk. I dug up the old website for the department, and I have no idea what happens when you hit that button. I'm just dying to know, though. Probably something to do with tables or something. But anyway, I'm not one to talk. I shouldn't, this is my website from back then. I don't know, is Rick's movie ratings website still around? Oh, what a shame. All right, so actually my website hasn't really changed that much. Has a different color and a different picture. But, so I was trying to find some pictures from back then, and I couldn't find any pictures of us working. It's just here we are at a party. We're doing karaoke at Mar Vista Lanes, which I don't think exists anymore. And here's a picture of some of the members of the department who entered in 1999. And I just thought it was interesting to see kind of where they are now. Julia Friedman, or Simard now, is a professor at Stanford. Stephen Erickson's a senior research statistician at RTI, and it's unbelievable because they got him to wear a suit. And Ivan Asensio is an assistant professor at the University of San Francisco. Would you have believed that, Jan? Anyway, sorry, that's enough inside jokes, I think. So that's the fun part of the talk. Now for the boring part. So, in case you don't know, this is where I work. This is the Johns Hopkins Bloomberg School of Public Health. Our motto is that we're protecting health, saving lives, millions at a time. Because, those doctors that work across the street, they only do save lives one at a time. I mean, they can't compete, right? So, what do we do in biostatistics? It's a little minor variation on that, right? So I don't think I need to tell anyone here necessarily about how things have changed in the last 20 years, but the measurement revolution has happened, or is happening. This is just one graph to depict that, which is the price for sequencing the genome, which is now, it's down to 1,000 for sure now. This graph's a little bit old. This is my colleague, Brian Capo. The number of things that we can do to him is really kind of incredible. We can lay mesh networks on his brain to measure the electric signals of his neurons. We can take magnetic resonance imaging. We can stick some Fitbits on him, measure his movement through accelerometry. We can look at his genetic information. Even while he's sleeping, we continue measuring with polysomnograms, things like that. And so at no moment in the day is he free from measurement, right? And not only that, but we can take him and we can apply these kinds of technologies to whole populations of people, right? So there's all kinds of data coming in. So to paraphrase a famous saying, data are eating the world, but the issue that I want to talk about today is that the analysis of that data has not yet caught up to the volume of the data itself. And I want to talk about why that might be and what we can do about it. So a couple more kind of milestones or kind of signposts, so to speak. This McKinsey report, talks about the critical shortage of data talent, data geek talent. And the primary problem with this report is that it only projected up to 2018, so I can't use it in talks anymore. But thanks to PricewaterhouseCoopers, they came out with a report that projected for 2020, so I can talk about this for another year or so, with 2.7 million postings for data science and analytics roles. And in 2015, there were more job postings for data science and analytics than for nursing and truck drivers combined. So a couple other things that are happening in the world is, you may have heard, there's a replication crisis. Things, the source of which in part can be potentially attributed to kind of flaws in data analysis or problems in data analysis. There's also, you have to worry about the fact that the people who study replication crisis are subject to the same problems that they are criticizing, which is that they can hype things up more than perhaps is warranted. So, a couple of challenges, just to summarize quickly. The data analysis is everywhere because data is everywhere, right? So, and everyone has become a data analyst whether you like it or not. You're pretty much forced into the situation. So, of course, the training of data analysis is important, but there's very limited bandwidth, right? So you think about how many postings there were going to be in 2020, 2.7 million. We are not training data analysts in the millions, right? The biggest programs around the country are training people by the hundreds, maybe thousands at this point. But whatever the number is, ASA does a survey of all the programs and say how many graduates there are. There's a mismatch between the demand and the supply. So, and last, I think our understanding of the data analysis process is quite narrow, and so that's what I want to talk about today. So, the two questions I want to talk about are what is a successful data analysis? What is how do we define what that means? And then what makes for a good data analyst? So meaning like a person who analyzes data, how do you know if they're good or not? So there's many other questions that I think are interesting, but I'm just going to focus on these two because Mark said I only had 4 hours to give this talk, right? So try to limit it, really. So back in 1991, there was a National Research Council report it was called The Future of Statistical Software. And in that report, Darryl Pregman had his own kind of paper, so to speak. And he wrote this, which said, throughout American or even global industry, there's much advocacy of statistical process control and the understanding of processes. Statisticians have a process they espouse but do not know anything about. It is the process of putting together many tiny pieces, the process called data analysis. Not really understood. And which I found useful because I think it's in some ways still true today, even though it's many years later. So any discussion of the so-called future of data analysis would be remiss if it didn't, I think, make at least reference to this paper by John Tukey, which he wrote in 1962 in the Annals of Mathematical Statistics, now the Annals of Statistics. And if you haven't read this paper, it's a worthwhile read. It's a long read, but it's worthwhile, I think, at the end of the day. And one of the things he talks about is how we should teach data analysis, and in distinction from what you might think of as statistics, is that we should teach data analysis like biochemistry with emphasis on what we've learned, with relegation of all question of detailed methods to the quote-unquote laboratory work. All study of detailed proofs or comparisons of ways of presentation would belong in the laboratory rather in the class. Now, he doesn't really specify what would go in the class. He only specifies, he just basically says all statistics should go in the laboratory. But he doesn't really go into detail about what should go on in class. And but I wanted to talk more. I'm going to talk later about in terms of how do we know what we've learned in data analysis, and how do we learn that information. So, main points I want to make in this talk are: the first is that we need to draw a kind of bigger picture of what the data analysis process is, and it's not because we don't know what that picture is. It's just because I think we have, in some ways, selected to narrow the scope on our own, and then we need to own that training that kind of corresponds to this bigger picture. I think it'd be useful to define what success and failure mean in data analysis, and to think about what it means to design data analyses to be successful. And then how do we learn lessons from failure? So once we know what failure means, how do we learn what those lessons are? Okay, so this diagram, I'm guessing many of you have probably seen something like it, if not this literal diagram. So this comes from Hadley Wickham's R for Data Science book, and I think it depicts something that many would agree is something like a data analytic process. You take data, you import it, you tidy the data to make it kind of usable, analytic, and then you go through a kind of washing machine cycle where you transform the data, you visualize it, you model it, transform it, you kind of go through the data, and that's maybe what you might call exploration. And then you kind of communicate some findings, right? So I think most statisticians would not disagree with the general vibe of this picture. They may change the words or maybe add a few things here and there. If you were particularly, radical, you might say, well, there's a question that starts the process, right? And you might even acknowledge that there's people on the other side that are actually, looking at the analysis, right? So the problem I have with this diagram is that it's rather narrow, right? And it doesn't include some of the fundamental aspects of a data analysis which don't involve the data, okay? And so the way I kind of like to look at it, you got to keep the washing machine, right? That's essential to all data analysis here. But the other key things, and we can talk about exactly how many other things there should be, but we still have the data, we still have the tidy data, right? We still have the results. But of course, now we've got the question, we've got contextual information, and we have resources that go into any data analysis, and we have the audience here. So the audience, I'll get to later, it's over here, it's also over there. Now, the key thing about this diagram, I think, is that this diagram, when I take out the data, this diagram, I think, makes sense, right? You ask me a question, I'll give you an answer. That is easily done. It happens every day at even the highest levels of government, right? It's not invalid in that sense. You ask me a question, I give you the results. It's not data analysis, right? But it's the diagram can be executed in some sense. This diagram does not make sense, in my opinion, and is not really valid because the data going in and just coming out does not produce anything of real value, I think. And so this diagram is basically, it kind of encompasses the idea that the data are just a bunch of numbers, right? And so if we want to think about what is the data analytic process, it has to include all the things, I think. And I think this is summarized quite well in this book that is just coming out called Data Feminism by Catherine D'Ignazio and Lauren Klein. And they ask, do the numbers ever speak for themselves? The short answer is no. The long answer is no. So that's why I think all this stuff has to come together as part of the data analytic process. And as much as we might like to kind of condition on or assume this stuff out, I think it's getting harder and harder to do that. So Make sure yeah. So the next thing I want to talk about is this component here, which is the audience, right? So there's two kind of people or roles or actors that I want to think about. One is the audience, like we're in California, so we'll talk about actors, right? So there's the audience, it's the person who kind of receives the analysis, and then there's the analyst who does the analysis, right? And the relationship between those two people, okay? So that's going to play a role in what I characterize as the success of a data analysis. So what is the kind of, how do we start to think about this? So the first thing that I think is, in retrospect, obvious, but I never really thought about, is that data analyses, you do not go into the forest and walk into a data analysis, right? They don't occur naturally, right? So anything that doesn't occur naturally has to be created by a person, right? And in that process of creation, we have to design it, right? And by designing it, what I mean is that choices have to be made. Decisions have to be made to do something and not do other things. And so that is the critical step, I think, the first step of thinking about what a data analysis is. It has to be constructed and designed by a person, like a data analyst, right? So, so in that sense, that I think this notion of design thinking is actually very critical to doing data analysis. And there's a lot of literature on design thinking, and two of the things that they focus on are, first is identifying the problem, and what I would kind of literally map to, in statistics, to the idea of exploratory data analysis in the kind of Tukey style of exploratory data analysis. And the other is building the solution, which I think we do focus on quite a bit already. This is kind of executing models, thinking about uncertainty, building a narrative, talking about communicating results. So how do we do this does depend on who the audience is and what their wants and needs are, okay? So just like in any good movie, every hero has wants and needs, right? And they'll usually tell you what they want. That's easy to figure out. They'll just tell you what they want. But any good data analyst tries to figure out what it is they need, okay? And that's a hard part. It's part of the design process. And so I think if you think about other things that we design, like this chair over here or maybe this podium, they are useful or not. And what makes them useful are, it depends on a lot of different factors. Maybe the chair has to be comfortable, the podium has to be not too tall. So there are a lot of factors that we think about when we evaluate whether an object that we construct is successful or not. And so those kinds of things are, it's useful to think about, well, what are those kinds of things for a data analysis, okay? So, so just to kind of lay things out a little bit, the way I see it is every analysis has two key roles. The first is the analyst, and the second is the audience. And they may be the same person in some cases, but often they are separate people, right? So the basic thrust of what I want to say is that both the analyst and the audience weigh a set of principles on which they kind of evaluate or characterize the data analysis. And I'll give some examples of what these principles are. But these principles, from the analyst's perspective, they help to guide the construction of the analysis. And the bottom line is that I think a successful analysis is one where the audience, first of all, they accept what the analyst has done, and they agree on the weighting of the principles chosen by the analyst. And we can talk about how this occurs literally over time, but at the end of the day, there has to be some agreement on this analysis was constructed according to a set of principles that I agree with. So what's the point of these principles? So they obviously reflect various qualities of the analysis. You can think of a kind of multidimensional space. Every principle is an axis in that space, and so they serve to guide the development of the analysis. So if we weight one principle more than another, then that will change how we do the analysis. They have to be observable from the output of the analysis, so they're not some latent thing that's in your brain somewhere that we'll never be able to know. And it'd be nice if we can measure them, even roughly, or categorize them in kind of a low, medium, high sense. And I think trained people should reasonably agree on what their values are in a given data analysis. So one, for example, could be the notion of exhaustiveness, right? So in a given analysis, for a given hypothesis or question, there are going to be a variety of ways to address that hypothesis, that question. And you may make a plot, you may make a table, you may calculate a statistic. Is there something else you can do? Then maybe that's it. So but even within those three categories, there's a variety of ways that you can think about how you would execute that strategy. And so if you do a lot of those things, that is, in some sense, more exhaustive. And if you do fewer of those things, it is less exhaustive. Now, the key is that I don't want to characterize this kind of spectrum as like one side is good and the other side is bad. It's just that one is over here and one is over there. If you look at a car, for example, you can talk about the different colors that the cars might have. It's not like red is better than black, it's just a different color, right? Or you might talk about, how fast it accelerates, You might need a high acceleration in some situations and you might not need it in other situations, right? So this is the kind of idea I'm thinking about in terms of what makes a reasonable principle for data analysis, that it's a characteristic that we don't necessarily measure good and bad on. It says that one way to characterize what was done. So some analyses have 1 million plots, and that's very exhaustive. Doesn't make them good. But sometimes you do want to see a lot of plots because you're at a different stage of your kind of analytic life, and you need to see that. So another one I think is probably more familiar to people is reproducibility. And so this, and I know there's some confusion over what this word means sometimes. So basically I'm thinking you have a data set, you have an analytic set of elements that you do for analysis. If I give you that data set, I give you the exact same set of elements, the code that executes that, you should get the same result, right? So on the high reproducibility, on the right side means you get the exact same result from two different analysts with the same data and the same kind of code. Low reproducibility would be you get different results for the same data and the same code. So there may be meaning that there's some hidden thing that wasn't executed that got you a different result. So again, I think reproducibility, we generally think of as being good or bad, but I do think there are situations where reproducibility is less important, and some situations where it's absolutely critical, and that can change depending on the situation. So I think reproducibility is just another one of these kind of principles that I'm talking about. And there are a few others. Stephanie Hicks and I have written a paper to kind of outline some ideas for what these other principles might be. So what is a successful analysis? So these are some of these other principles. I won't go into detail, but I'm happy to talk about them later. Skepticism, skeptical, transparent, data matching, second order. These are all principles that I kind of imagine being on a continuous line, right? So you can score them on some continuous value. And I have a set of weights that I put on these various things, given the problem, given the situation, given the data set, and given who I think the audience is going to be. And if I and the audience agree on kind of what those weightings are, then that's what I define as success, okay? And the great thing about doing a talk in 2019 versus 1999 is that you can use emojis, right? So it's super useful. Now, if the audience has a totally different concept of what is important to them with respect to these various principles, then they have different weights for what they think is important or to this given analysis. And so if we disagree on what those weights are, then that is the opposite of success. That's a failure. So that's kind of like the general framework. There's a lot of kind of other issues to think about in terms of, well, how does the analyst know what the audience is going to be looking for? Can they communicate? Do they share information? Do I adjust my weighting of these principles? Because I know, oh, they really value, they want to see a lot of plots, and they want to see different pictures of the data, so we'll make lots of plots, we'll make lots of pictures. But maybe they hate pictures, and the pictures aren't essential, and so we won't. But that's kind of like a separate issue, I think. So, but that's the basic idea. There has to be there's two actors, there's a set of principles, and they have to match. And so now I think I've talked about this idea in a few different places, and the biggest issue that people seem to see is that it seems like a recipe for just giving people what they want. Like, I want p less than 0.05, so here's p less than 0.05, or something like that, right? And that's not how I see it, with the idea being that, like, so this, I don't know if anyone recognizes this bridge, it's Coman-Narrows Bridge, which collapsed many years ago, and because of the way it's constructed, when the wind would blow, it would kind of vibrate up and down like this. There's some amazing video on YouTube of this bridge kind of gently swaying like that. And you know, someone might say, I want a bridge that, you know, swings up and down. That seems cool, right? Why don't you give me that? But, you know, a good engineer is not going to violate the laws of physics because they know it's going to collapse, right? And so there are some basic inherent kind of intrinsic kind of, I kind of refer them as like laws of physics, like things that you can't break when you construct, for example, a bridge. And I think the same is true in statistics, right? When you're analyzing data, you don't just do anything, right? There are certain things that we know already that we learn in all of our classes about regression modeling, about testing, hypothesis testing, you know, all those kinds of things. And we're not going to just deliberately violate them, right? So otherwise, we end up with a collapsed bridge. So the other question I often get is whether success equals winning, okay? So this is on an article from the Wall Street Journal. Came out last year, I think. It was about a story about Netflix. And I'm just guessing everyone here knows what Netflix is, but they produce a lot of original TV shows and movies. And the way that they market them depends a lot on data. They do a lot of testing of, you know, what kinds of advertisements are useful, are successful in terms of getting people to watch the shows, et cetera. So that's the kind of the data side of the business. The other side of the business is all the people who are in charge of kind of getting contracts with these famous actors and directors. And some actors insist that their image appear on every ad, right? And then the data team says, well, when we put that image, like, nobody clicks on it, right? And so then what do you do, right? So anytime you see an article about, you know, who's winning, A or B, I mean, the reason why that article exists is because the losers are talking, right? That's the only reason this happens, right? So and so I asked my friend Hillary Parker, who we have a podcast with, she works at Statistics. I said, who do you think's losing? And she said, for sure the data team is losing. There's no question about that, right? Now, they're losing in the sense that their data provides evidence for a certain type of action, right? Putting a picture of a certain person in the ad. But the rest of the company is saying, okay, we agree that that's what the data says, but we can't do that for reasons A, B, or C, right? So the data team, in some sense, doesn't win that argument. But in my understanding, is still their analysis, which I've never seen, so I don't know what's actually going on. But my assumption, if that's what's happening, then that data analysis is successful. Because it's not like the Hollywood side of the business is saying your analysis is flawed. They accept the kind of the output of the analysis, but they can't act in a certain way. So success is not about winning, although we can discuss that perhaps later over beer maybe. So I think the bottom line I have here is that data analyses should be designed explicitly based on a set of kind of shared principles. Identifying the relevant principles requires consideration of the audience. Now, because the audience is always changing, right? And so that means that the analysis in some sense is also always changing. Now, practically speaking, it's not always possible to do a totally different analysis for every single person you talk to. But in principle, that is shifting with the audience. Of course, the basic rules of statistics and mathematics can't be broken. It doesn't mean you can just do whatever you want. And also, even a good analysis can fail in the sense that, not in the sense that it can fail in the sense that people don't act on it, if you're expecting people to act on it. Okay. So the last thing I want to talk about is how we learn what to do. And I just bring back this quote from Tukey's paper, where he says, you know, we should talk about what we've learned. Now, part of the problem with data analysis is that it's actually very difficult to do this, because part of learning anything, really, comes down to learning from mistakes and from failures. But when data analyses fail, we usually don't know about it. Maybe they're not published, or maybe no one talks about it, or something doesn't work out and we move on, or we just kind of throw it out and start over, right? So so those details are usually not public. They're not recorded in any real way. It would be probably impossible to record every single action of every single data analyst everywhere, right? I mean, it's not practical. So we can't really review it, at least publicly. Often when there is information about data analytic failures, I think we often draw the incorrect lessons because we have incomplete information. And then we often focus on assigning blame. So who messed up? Who did the wrong thing? Who used this method incorrectly? Right? And that is not a particularly productive way to learn anything. And so I think that's part of the problem. So anytime we kind of have information about this, it's usually because we were involved in the process, right? So we actually were involved in the data analysis, so we have insider information. Or there was some essentially investigative journalism that occurred that unearthed some details. And even then, it's usually not all the details, as I'll show you in a second. So I think analysis of failures, they tend to either focus on very narrow proximate causes or very kind of vague environmental causes, right? And so the examples are classically the misuse of p-values, right? P-values are the reason why data analyses are messed up, right? That's a very narrow proximate cause. It's at the very end of the process, right? But we get to see that, right? And so that's kind of like where the street light is shining its light, right? The other is funding levels for people are going down and there's pressures to publish, and so that's kind of a very vague and general kind of environmental phenomenon, right? And the other is people do not have enough training in statistics, right? So, but a lot of these so-called lessons don't lead to any valuable interventions, right? So, for example, with the p-values, what's the intervention implied there? We don't use p-values. We use confidence intervals instead. What are we supposed to do with that information? Or for things like funding levels, there is an intervention that we can think of, which is increase the funding levels. But let's be it's a very difficult intervention. I guess is the way to put that. So for any kind of analysis of failures, and there's a long and very kind of detailed literature on this issue, you need a detailed timeline of what happened, right? And then you have to have a very open and honest discussion from all of the participants, okay? So if you look at famous failures like the Challenger space shuttle, the Columbia space shuttle, other major kind of disasters, what they have a commission, they get together, they map out every second of that timeline. And they talk about what happened when, who made what decision, and there's no discussion of whose fault it is, okay? So two case studies that I want to mention. One is the Harvard Six City studies and the American Cancer Society studies. These are air pollution studies that occurred in the late 90s, late 90s. And they are, even to this day, some of the most important air pollution studies ever conducted. So they were some of the early studies that really kind of showed that air pollution is associated with mortality, which is a pretty striking claim because mortality is a pretty striking outcome. And so, and it wasn't like a little bit associated. So they said the adjusted mortality rate ratio for the most polluted, when you compare the most polluted city of these 6, in this case, to the least polluted city, the adjusted mortality rate ratio was 1.26. So that's huge. That's huge for anything, much less air pollution, right? And so, frankly, unbelievable. And I think rightfully so, nobody believed it, right? So there was a follow-up study with using a different population, a much larger population that was based on a cohort that the American Cancer Society tracks for smoking-related kind of reasons. But they used this cohort and kind of matched them with air pollution exposure. And they found that when you look at when you compare the most polluted areas to the least polluted areas, there was an adjusted risk ratio of 1.17. So not quite as big, still enormous, and if true, very terrifying, right? So now we have these 2 studies, and they involve hundreds of thousands of people in these studies. And these were done in the late 90s, right? That's a long time ago. There have been many studies since then. And so, but at that time, the EPA was looking to reassess the evidence for particulate matter, or dust. We call it particulate matter because it sounds fancy. But for the health effects in 1997, and in 1997, there was still question of whether this was there was any sort of association between particles and health. And so these two studies, they weighed very heavily on their assessment because they were the largest at their time. They were in the United States, and there wasn't much else to look at in terms of evidence. So members of Congress and the automobile industry, power plant industry, they really scrutinized these studies because they knew that regulation would come down based on the evidence presented in these studies, and they forcefully challenged all of the results and claimed that the analysis was not done correctly. And what they wanted was the data and the code. Well, they didn't care about the code. They really wanted the data. But the problem is the data was all person identifiable. There was no real mechanism for giving anyone the data. So what happened was the Health Effects Institute got involved. The Health Effects Institute is a nonprofit that funds air pollution research, and I guess I should say that I do a little bit of work for them. So I do think they're a good organization. But they offered to kind of be a trusted third party. They took the data, they got an independent set of researchers to look at the data, to redo all the analyses, and they published this report in July of 2000. And basically, what they found was that there was some sloppy data management. Given the size of the analysis of the study, it wasn't as bad as it could have been, but the analysis was not fatally flawed. All the results were basically reproducible. They did a ton of other analyses on top of what was originally done. None of these sensitivity analyses really invalidated kind of what the original findings said. There was not a lot of significant sensitivity to the models. So this highlighted to me kind of what I sometimes call Schrodinger's analysis, which is that the same analysis can be a success or a failure depending on who's looking at it, right? So the industry people didn't like it. Now you can ask why they didn't like it. I think we can think about why they didn't like it. But remember, they criticized the analysis itself. It's not like they of course didn't like the outcome, the conclusions, I should say, but they criticized the analysis itself. So the academic scientists largely thought that it was a reasonable analysis, but they, interestingly, they also did not believe the conclusions, right? Because the conclusions were really out there, right, for the time. So the idea is that there's a trusted third party to kind of mediate this disagreement. And the one thing that's interesting about the Health Effects Institute is that half their funding comes from the EPA and half their funding comes from the automobile industry. And so there was some element of, okay, the automobile industry can say, well, we're actually kind of involved in this process a little bit because we help fund this institute, so we can, in some sense, trust them more than if some random person came along to reanalyze the data. So trust actually plays an important role in whether you're willing to accept kind of the findings of an analysis or willing to accept the analysis itself. And I think that is a tricky one, but it's a direct result of kind of human beings have to build and construct this thing. The last one I think is a little bit maybe more well-known in our field is the Duke saga. So this now goes back many, many years, but in 2006, this paper came out in Nature Medicine, which basically claimed to use a microarray-based predictor to predict whether a person would respond to chemotherapy, right? So if true, again, kind of amazing, right? So eventually it was retracted, just a kind of spoiler alert there. But so Keith Baggerly and Kevin Coombs at MD Anderson Cancer Center, they were very interested in reproducing this result because if true, it would be amazing, right? So, but they immediately found very basic data management problems, too many to really go into any detail. But even things like switching the labels of the outcomes, so the people who were sensitive to chemotherapy and not sensitive to chemotherapy, their labels were reversed, so now you're predicting people who are not going to respond. Anyway, there's like so many problems, right? And there was strong evidence of so not just kind of mismanagement and kind of incompetence, but really there was strong evidence of deliberate fraud. So there's a long history to this. There was a feature on 60 Minutes talking about this episode. Kevin Coombs and Keith Baggerly got their picture in the New York Times, most famous biostatisticians in the country. And ultimately, the Institute of Medicine convened a committee to talk about, well, how do we think about omics, genomics, proteomics, metabolomics, whatever it is, and their translation into the clinic. So the reason why this whole thing kind of came to light is because they were doing clinical trials based on this predictor that was totally flawed, right? So they were going to assign different treatments to people based on a predictor that was totally flawed, right? So that's the thing that this report focuses on, which is that we don't want these things coming out of the computer, jumping out of the computer and going into the clinic without some sort of process, basically. So they talked about many things, but one of them, some of the key findings were that when these predictors are developed, the data and the metadata used to develop the test should be made publicly available. Can't disagree with that. The computer code, because these are algorithms that we're talking about, should be fully specified, and then all the procedures should be made available to the public. And then on top of that, ideally, all the computer code that encompasses all the steps of the computational analysis, including all the data processing, that should be made available too. So I think it was unequivocally a strong call for reproducibility and transparency. So the IOM report, if you look at kind of what happens, the research is done, right? Then they publish a paper. And then how do we make that reproducible? We make the code and the data available, right? Now, the IOM committee did not want this to happen without at least having some sort of standards and process, right? So reproducibility is one of them. There were other ideas that they proposed too. They don't want us going into human clinical trials on a predictor that I just came up with yesterday and seemed pretty cool, right? So there has to be a process. But the problem is that this does not, in some sense, do anything, right? These flawed predictors can be written and developed all the time. This doesn't really say anything about that, right? It just says don't use them in clinical trials. So the question is, what do we do? How do we kind of intervene on that box there? Okay, and most people said, well, reproducibility, right? But the problem is reproducibility is all the way over there, like long after the research is done, right? And so what lesson do we learn from this? So far, it seems like reproducibility is important. People need to be trained in the methods that they're using. There's, people talk about publication pressure and the need to get into these glamour journals like Nature and Science. There's funding, there was conflicts of interest, there's all kinds of lessons learned. But in my opinion, these are not the right lessons in the sense that if we addressed all these things, the same thing can happen tomorrow. And so it was interesting to find out later, much later in 2015, that a memo came out written by this person, Brad Perez, where he was a lab member in the lab of the person who kind of was the senior investigator at Duke. He was a medical student there, just kind of rotating through really. And he was involved in some of the research on the predictor development. And he wrote, at some point, he recognized that there were a lot of problems with predictors in terms of their ability to actually, in kind of an unbiased way, predict outcomes, right? So he said, at this point, I believe that, this is in 2008 now, I believe that the situation is serious enough that all further analysis should be stopped to evaluate what is known about each predictor, and it should be reconsidered which are appropriate to continue using and under what circumstances, and then, et cetera. And then all claims of predictor validations should be independently and blindly performed, which is like, it's a totally reasonable thing to say. Any statistician I think, would see that. The point is that, first of all, this was 2008, so it was after the original paper, but before a lot of other papers. That these analyses, so there was a lot of discussion of how these analyses are so complicated, and so the result is that there should be more training, right? But they weren't that complicated. They were, in fact, so not complicated that a medical student kind of understand what was going on and could recognize that they were flawed, right? So that's point number one. There wasn't insufficient expertise. He had the expertise, right? There were clearly lab/institute cultural problems that kind of basically he wrote this long memo and it was ignored, right? So I think from the data analyst perspective, the key breakdown here is in the communication between the various people on the team, right? And that is like that is probably the number one indicator of a data analytic problem, right? It doesn't actually have anything to do with the data, right? Or the methods for that matter. But it's a key thing to be have your kind of antennas looking out for. Making these analyses reproducible would not have done anything. They were already reproducible. They could reproduce them in the lab. That's how he knew that, that they were messed up, right? So making them more reproducible, I don't think would have made any difference. Furthermore, it doesn't change the fact that reproducibility is something that happens very long. It's very at the end of the process. Right? So I think here, the lesson that ultimately I think is learned is that the analysis depends on the relationships between the people involved in the analysis itself. It depends critically on that. Because they could have stopped this and gone through. They probably, I think in the counterfactual world where someone actually listened, they probably wouldn't have published the same paper or any paper at all for that matter. But that didn't happen. So this took a long time to play out because none of us were in that lab at Duke, at least I don't think. So this all had to kind of come out in a very kind of small-time publication called The Cancer Letter, where one guy, who writes that whole newsletter, got in touch with a lot of these people in the lab and had to dig up all this information. It was essentially a muckraking operation, right? So we shouldn't have to do that for every single, just to learn what happened, right? But at the end of the day, it kind of is what we have to do. So I think that's an inherent problem. So what's a successful data analysis? I feel like I've discussed this, at least what I think is the answer to this question. What makes for a good data analyst is it's obviously the other side of the coin. What are the qualities that we want in a data analysis? How do we train them to produce successful analyses, right? And I think there's 5 things that I can think of, and this is kind of essentially the summary of my talk, which is that I think a good data analyst applies design thinking to data process, right? Because they're building this thing called the data analysis. They have to design it in a way that it will be successful. I didn't talk about this much, but it is in some sense related to reproducibility. They have to manage the workflows of the data and the processing of the data, the transforming of it, where it comes and where it goes. They're in a position to kind of do that in a way that's best for answering whatever question they're trying to look at. They have to negotiate these human relationships, partly as part of the design process, right? Because you have to identify what's the context, who are the people that need this analysis, what do they need, what are their kind of wants and needs. They have to allocate the resources to do this analysis. And so there's typically many different relationships that have to be negotiated through this process. Of course, they have to apply statistical methods to quantify evidence. And they have to do that in the best possible way. And then lastly, which I didn't really discuss today, but we have to transform all this information that we do in data analysis into narratives and stories that people will be willing to listen to. And so, so I think there are a number of these bullets that I think we don't really focus on in our training of data analysis. And I think you learn them typically on a kind of apprentice model, right? You work with someone, you work with your PhD advisor, and then just through observation and through feedback and through living life, you see what works, you see what doesn't work, you fix what doesn't work, and you kind of iterate through the process. And this takes typically 3 to 4 years, right? So that's fine, it's not an invalid approach, but it's not a highly scalable one, right? And so I think if we want to think about training more people and kind of meeting in some way the demand for data analytics skill out there in the world, we have to think about, well, what is the actual thing that we're doing here, and how can we more efficiently deliver that training process to a larger number of people. So that's basically what I want to talk about today. So thank you very much, and thanks to Jan for this seminar series.